Good morning, people. We have please lower down the volume. We have crossed the midway mark, okay? And I'd like to, just recap what we have done till date. So we are somewhere here. Today we are here. So it's 9 includes one class which we missed. So that was on 14th February we missed. And in fact, we have just over today we are on the 8th class. And probably, if we recap, we have nearly finished half the mark. And the remaining half I have summarized in this sheet. Okay, so somewhere over here is exceeds the 15 classes is the stability of slope. So if we are able to, volume is gone. If you are able to, uh, you know, uh, uh, squeeze in some of the topics, I think we can just drag this up. Let me just right click and allow download. So just for your own summary, you can go back home and review this sheet. In the previous class, we had started off with the topic, on soil with water. We had looked at the concept of effective stress. In fact, there was an example which we hurriedly did towards the end of last class. And one section of the example was on when what happens if the water table is above the ground surface. And I had left this part for you to do it at home. Now just let us review what was done. Okay, in this particular example, there was one case, if this is the ground surface, the groundwater table was at the surface, and if you were asked to find out at a depth Z, any depth Z, what is the total stress. When I say total stress, in fact, we are looking at total vertical stress. We will look at horizontal stress uh, later. If given a chance, we do slope stability. But in this case, just as an introductory part, we are looking at total vertical stress. So at this depth, the pore water pressure at this depth, and as a result, the effective stress at this depth. Remember, the total stress was related to effective stress plus the pore water pressure. Okay? So what's the total stress, which is sigma over here, equals to, if this is gamma, because the water table is at the surface, so it's gamma saturated. Okay, we assume that all the voids are filled with water. So total stress is the saturated unit weight of this soil times the depth. So it's Z gamma, Z times gamma saturated. What about the pore water pressure, U? It's in a sense, it's simply the unit weight of water times the depth you're looking at. So in this case, the depth is still Z, and the unit weight is gamma W. Hence, the effective stress sigma prime, which is total stress minus the pore water pressure, equals to Z gamma sat minus Z gamma W. Some of us, in fact, some of this, our people in this area try to take the Z common outside and write gamma sat minus gamma W. This gamma sat minus gamma W in the first class we did was gamma prime, which is the point unit weight. However, I would like you to just stick onto this concept just for simplicity. It makes our life much simple if we just, evaluate what is gamma saturated minus the Z times gamma water. Let's take the other example wherein the water table was above the surface. So in this, the other case was if this was the ground surface and your water table was, say, a distance of, this is Z, let's call this as Y above the surface, you're still interested in the point which is at depth Z. Okay, that was the last case in the example. If you would have tried this at home, the total stress at this depth includes the weight of this water plus the saturated weight of soil. So in other words, if I follow the same analogy as the previous example, we had Z times gamma saturated. So this is gamma saturated. It will remain saturated. Okay? Plus Y times gamma of water. Okay, that is the total stress. What about the pore water pressure? Pore water pressure equals to total depth, Z plus Y times gamma water. And if you're interested in effective stress, which is total stress minus the pore water pressure, I get Z gamma sat plus Y gamma W, that's the first case, minus the second case, which is Z plus Y gamma water. If I try to open up the brackets inside, I get Z gamma sat plus Y gamma W minus of Z gamma W and minus of Y gamma W. If you look at this carefully, plus Y gamma W minus Y gamma W erode off, we get Z gamma sat minus Z gamma water. Look at this carefully, this is the same as this equation over there. In other words, if the water table moves above the ground surface, okay, at any level, the effective stress at any depth Z would remain the same. It does not change the effective stress. Okay? We looked at this problem, and we also looked at a section on soil capillarity. So let's review that particular section. If you have any questions in between, I request you to raise your hand. There is an icon over there. Please do raise the hand. Okay? In fact, your feedback is pretty important for the success of this entire program. Okay? So we looked at this section on capillarity. In fact, there was a photograph on the first slide. I missed explaining this. This photograph is from Nikita Ertek, 1964, I think. Yes, it's there, 1964. It shows how the water had played a very significant role in the liquefaction. We'll come to this liquefaction, but it tries to explain how the movement of the water, the upward movement of the water would cause the effective stress of the soil to become zero. As a result, the strength of the soil becomes zero, or the buildings, anything which is shown on the photograph, simply collapsed. There was no structure distress. The structure was sound. Let me recap what was done. We started with the soil capillarity. Okay, we said soil capillarity. Okay, we have a mouse. We said the capillarity minuscule of the soil, it hangs on to the particle, meaning the particles are held together. There is a kind of adhesion, but we call this force as soil suction. The soil suction comes into place. Take an example of two particles which are shown over here. The blue color shows the soil capillarity, which holds on to the two adjacent particles. Okay? It does not allow the particle to move. Therefore, our previous study, we knew that the soil capillarity at this level would be minus Hc times gamma W. Depends how much is the soil suction which exists. So we have a negative sign times Hc gamma W. If you're looking at, if we say that this soil still remains saturated, but however the saturation is because of the soil capillarity. So we have an effective stress equals total stress minus the pore water pressure. Okay? In this case, the pore water pressure is because of capillarity, which is a negative sign over there. It results in an effective stress being increased by this magnitude, the magnitude of the soil capillarity. So what were the consequences of this effective stress increase? The very first one, the increase in effective stress would cause the increase in shear strength. In other words, if you're doing a direct shear test or triaxial or any other shear on a partially saturated soil, you would find that the strength of the soil to be higher than the strength otherwise you would have measured for a saturated soil or for a dry soil. So I repeat, if your soil has capillarity in between, the strength or the strength parameters would be greater. In other words, you have a case called apparent cohesion coming up. Now, many times, many of researchers argue that, the true cohesion of a soil is zero. Okay? So the true cohesion is the cohesion of the soil you measure when the soil is either completely saturated or completely dry. So for a saturated soil on one hand and the dry soil on the other hand, your true cohesion, this group of people say, is zero. Okay? And when you get cohesion, it's only because of the apparent or the soil capillarity coming into picture when the soil is not completely saturated or not completely dry. Okay? So let's move on. There were examples which we had to look at. A fine example of soil capillarity is at the beach. I have zapped in this cartoon. This cartoon shows, very close to the beach, wherein soil capillarity exists. You can easily walk over the sand. The sand will not sink in. However, if I go up the, away from the beach, you see that your feet actually start to sink in because there is no soil capillarity. There is no strength in the soil. Okay? So the feet start to sink in. And wherein the waves of the water come in and destroy the soil capillarity. If you try to walk over there, you see that your feet still sink in because the soil capillarity has been destroyed because of the wave action or the water coming in. Okay? Continuous water coming in and going. So that's a fine example at the beach. If you happen to make a site visit at the beach, you can see the extremes of soil capillarity existing. There is another example wherein, this is a good example wherein you see that there is some deep excavation. Okay? This figure, of course, shows an excavation, probably not more than 2 or 2.5 meter depth. But if you're looking at such depth excavation which are not supported, it is only because of soil capillarity. So over here you have an example wherein some sides of the wall of the vertical cut will face the sun. If you look at the sun which goes up from the east, sets in the west, so there are two sides of any excavation which more or less would face the sun during the day. These sides are prone to collapse because the heat of the sun would destroy the soil capillarity, and as a result, these sides are prone to collapse if not left supported. If not left supported for a long period. So it needs support. Whereas the sites which remain under shadow, I would say they would need less of support, or they can remain unsupported for a longer period because of the soil capillarity. Okay? Let's move on to the next case, wherein an example of bulking of sand was there. Bulking of sand exists because of capillarity. The capillarity holds onto the soil particles, especially sand, into a honeycomb kind of structure. So you have a honeycomb, meaning the beehive kind of structure, which leaves gap. So this gap, in fact, causes the volume of the sand to increase. That is why it is always advisable not to buy sand when you're buying sand in terms of volume, which has a water content of about 6-8% or so, because it causes the sand to bulk. So you pay more for less sand. There's another example of capillary siphoning, wherein the water from the upstream of the dam would cross over the top of the dam or the crest of the dam to go downstream. So even if the water table is lower, so because of the siphoning, you can see that the water table with water which is held by the dam, in fact, can go down because of the soil capillarity. Okay? So before we continue to the next section, which is permeability, I would like to do one more example. One more example where we had a problem sheet where we looked at stress distribution, just to clearly understand, our soil capillarity. I have a column over here. Okay, let me just right click and allow download. Okay, so you can download this question. We'll spend the next 10 to 15 minutes to solve this problem. In a sense, what this problem shows is, please, if you look at the figure, it shows the ground level. The ground surface is shown as 0 meters, and going down the surface, it's -1 meter, 4 meters, 6 meter, and 9 meter. The water table is at 6 meters below the surface. That's GWT. We also call this as the phreatic surface. from 6 meters to 1 meter below the surface, the ground is saturated, okay, because of the capillary. So over here, below this is the groundwater table saturation, but from here to above is the capillary saturation. Okay. Thank you. So from there to there is is the soil remains partially saturated with degree of saturation of 85%. Okay. And you're asked to find out what is the stress distribution at 0 meter, 1 meter, and so on. Okay, let's solve this. Okay. Right, if you have understood the question is very similar to the previous one, except that in this case, you are asked to find out the stress distribution when the soil capillary exists. Okay. Now, I would let you live in peace. You can, copy this question later. We would not like to use this expensive video time just to show you a question and you can, copy down in your own pace. Please download this when you're back home. I'll try to solve this. I'll remove this paper and solve it. Okay. So the first part is, okay, over here you have been given the void ratio of the sand, the specific gravity of the sand. So below this broken line, that means from the broken line to this level, the sand is saturated because of capillary. The degree of saturation is 1. Over there, the degree of saturation is 0.85. So let's first calculate the bulk unit weight. If you recall, okay, the first class, we said gamma bulk equals to GS plus SC divided by 1 plus E into gamma W. Remember, we would be using this expression quite often. It's important expression. So gamma bulk for sand, which is partially saturated with 85% degree of saturation, you get GS. Okay, I can use this equation. I'll input the parameters. GS is given as 2.65 plus S is given as 0.85. Void ratio is 0.6. You get over 1 plus 0.6. Whole thing times 9.81. Okay. If you plug in your numbers, you should get an answer which is 19.37 kilonewton per meter cube. Okay, that's the bulk. What about gamma saturated for sand, which is from this level down to this level, which is saturated sand. So if you look at gamma saturated, I simply plug in S equal to 1 in this expression. I get 2.65 plus 0.6 divided by 1 plus 0.6. Whole thing times 9.81. I should get a number which is 19.93 kilonewton per meter cube. If you look at these two numbers carefully, gamma bulk and gamma saturated, the unit weights are quite close. This is quite often you see this in natural soil, the bulk unit weight and the saturated unit weight is quite similar. Okay? So what about the clay? Okay, let me bring in the sheet again. The clay, the void ratio has been given and the unit weight of the solids has been given. Okay, if I have to use the same expression as over here, what I need is the specific gravity. Okay, unit weight of solids is given. Can I say specific gravity? Okay, for a general expression is gamma solids over gamma water. This has been given. I can deduce this from this expression. Okay. So let's look at for clay. GS equals to 26.50 is given divided by 9.81. Plug in your number, you get GS equals to 2.70. Okay. So we now have GS can I say gamma saturated for clay? Okay, this should be equal to, again if I use the same expression as before, I get 2.7 plus, where are you, void ratio is 0.88 divided by 1 plus 0.88 whole thing times 9.84. If you plug in your number, you should get an answer which is 18.68 kilonewton per meter cube. Okay, now I have 3 unit weights. This is for clay, which is saturated. This is for sand, which is saturated. This is for sand, which is partially saturated. And we're going to use these numbers on the next page. In fact, the number चाहिए होगा. Never mind, I have it. It's okay. So the first part of this question was, what are the stresses at 0 meter depth? So let's look at 0 meters. So at 0 meter depth, the total stress sigma on the surface equals to 0. There's nothing above the surface, it's 0. What about pore water pressure? U equals to 0. Okay, again 0. There's no pore water pressure. Therefore, the effective stress sigma prime equals to 0. Total stress minus the pore water pressure. Okay. So what I'll do is, this page. What I'll do is, I'll write this down. The total stress, pore water pressure, effective stress somewhere over here. Okay. So at 0 meter depth, okay, total pore water pressure and effective. Okay, I'll just jot down the answer. Quickly jot. Total was at depth 0, total was 0, pore water pressure was 0, effective was 0. Remember, all these units are in kilonewton per meter square or kPa. Right? So I'll just pull off the sheet because for my record I need these numbers. Okay. What about the next part? The next part is at 1 meter. So 1 meter, if you look at this question carefully, it's capillary saturated at 1 meter. Okay, so let's evaluate what is the total stress, pore water pressure, and the effective stress at 1 meter. Okay, in this case, I'll just represent the sigma as total stress. Okay, I would not write this in English. The total stress at 1 meter equals the depth times the gamma bulk of sand. So that equals to 1 times 19.37 equals to 19.37 kilonewton per meter square or kPa. Okay. What about the pore water pressure? Pore water pressure at 1 meter, okay, equals to minus Hc times gamma W. Hc is the elevation measured above the groundwater table level and up to this level. Remember, this is capillary saturated. So it's from there to there is all negative. So this distance is 5 meters, I believe. So I have equals to minus 5 times 9.81. Which should give you a number which is minus 49.05 kilonewton per meter square. Okay. Just for your information, I'm surrounded by 3 persons, tightly packed at one corner. Okay. So what about the effective stress? Sigma prime. Effective stress equals to total stress minus the pore water pressure. So equals to 19.37 minus of minus 49.05. So minus minus become positive. In other words, my effective stress is now 68.42 kilonewton per meter square. Okay, so let me just jot down these numbers again. Okay, this is at 1 meter depth. Okay, so depth is 1 meter. I have my total stress is 19.37, pore water pressure is minus 49.05, and effective stress is 68.42. Okay. Oops, 68.42 goes over there. So let me just, this is 68.42. Okay, the next part is doing it at 4 meter depth. So 4 meter depth is at the interface of the sand and clay. Okay. Okay. So 4 meters would mean 1 meter of partially saturated sand plus 3 meters of saturated sand. So total stress equals to 1 times gamma bulk, that's of sand, plus 3 times gamma saturated of sand. It gives you a value of 1 times, I have a number 19.37 plus 3 times 19.93. You plug in a number, you should have 79.16 kilonewton per meter square or kilopascal. Okay, so if you look at this, the total stress, okay, in this problem remains the same irrespective of the soil is saturated by capillary or saturated by the being below water table. It does not matter. So just to put it in English, total stress remains the same irrespective the soil is saturated by capillary or by gravity water. Okay, this is quite an important statement. What it means is your soil, as long as is it saturated, your total stress will use, you have to use same the formula. What about the pore water pressure? U. At this level, you are 2 meters above the water table, and this 2 meters is saturated because of capillary. So I have minus Hc gamma W, the same formula coming up. That's minus 2 into 9.81, okay, which should give you a number 9 minus 19.62 kilonewton per meter square or kilopascal. So the difference between total stress and pore water pressure, that's the effective stress. This value should be 79.16 minus of minus 19.62. Okay, if you plug in your number, you should have a number which is 98.78 kilonewton per meter square. Okay, let's write these three numbers down, okay, on our wonderful sheet. Just going to copy this thing again. Okay, this time I'll use a black pen, which is, we are looking at 4 meter depth, I guess. Your total stress is 79.16. The pore water pressure is minus 19.62 and effective stress was 98.78. Is that correct? Yes. Okay, I've just made a column over there. Okay, just for the sake of convenience. The next level is evaluate the stresses at 6 meter depth. So remember 6 meters is at the groundwater table level. Okay. Total stress at 6 meters would be 1 meter of partially saturated sand plus 3 meters of saturated sand plus another 2 meters of saturated clay. So I have 1 gamma bulk of sand plus 3 gamma saturated of sand plus 2 of gamma saturated of clay. Okay. If I plug in my numbers, I get 1 times 19.37 plus 3 times 19.93 plus 2 times of 18.68. Okay, which should give me a number which is 116.52 kilonewton per meter square or kilopascal. Right? What about the pore water pressure? Okay, pore water pressure, you are looking at 6 meter depth. So pore water pressure at the phreatic surface or the groundwater table level is 0. Okay, recall pore water pressure is 0 at groundwater table level. Okay, if you remember, we looked at gauge pressure and absolute pressure. On all engineering terms, we will be using gauge because you're gauging with respect to atmospheric pressure, and gauge is a word you try to omit. You don't write gauge, so it's understood that U is 0. What about the effective stress? Sigma prime equals to 116.52 minus 0, which is 116 kilopascal or kilonewton per meter square. Let me write this on my wonderful sheet. That's my paper over there, and I'll still use my black pen. So we are at 6 meters. 6 meters, total stress is 116.52. Okay. Your pore water pressure is 0 and effective stress is 116.52. Okay. Let's look at the last one, which is the question says also evaluate the stresses at 9 meter depth. 9 meter is the bottommost part. Definitely, it's probably end of clay. Not sure, but it says 9 meter. Okay. So what about the total stress at 9 meter? Total stress would be up to the 6 meters plus the 3 meters of saturated clay. So up to 6 meters I have 116. I'm not going to redo this again. So I've zapped this number from the top figure, which is 116 plus the 3 meters of clay, which is 3 times, I think it's 18.68. Yes, it's 18.68. If you plug in your number, you should get 172.56 kilonewton per meter square. Again, that's your total stress. What about the pore water pressure? Pore water pressure, please look at this. Yes, this is the groundwater table. You are 3 meters below the water table. Okay, so 6 meters to 9 meters, this whole distance is 3 meters. So if pore water pressure should be 3 times 9.81. Okay, if I plug in my number, it's 29.43 kilonewton per meter square. Therefore, the effective stress equals total stress minus the pore water pressure equals 172.56 minus 29.43. Okay, this should give you a number which is 143.13 kilonewton per meter square or kilopascal. Okay, if I try to write this again on my sheet, okay, this time I'll go back to my blue pen. 9 meters. Okay, just let me drag this paper. So total stress at 9 meter was 117.56. Pore water pressure was 29.43 and the effective stress was 143.13. Okay, now the same question says, okay, it is question, let me bring back the question. The question says the stress distribution diagram. Okay, we need to draw the stress distribution diagram. If you would have followed the analogy as the last question, okay, this is the table which we have made effectively, that table. Okay, the same stresses. If I use a total stress, so at 0 meters it's 0, 1 meter below the surface it's 19, 4 meters it's 79, and so on. Let me just show you the total stress first. Please ignore the second and the third figure for the time being. The first figure, I'm not sure if it's clear to you. This is the depth. That is the first one. So I have 19.37 over there. The second depth was at 4 meter, which is 79. So at 4 meters I have 79. I have to draw this at an appropriate scale. So I just have chosen an approximate scale just to make this figure look nice. The next one is at 6 meter depth, which is 116.52. So that's 116.52. The rest one, if you scroll down 9 meter, let me scroll up, scroll 9 meter, it's again 117. So I have this 117 over here. Similarly, the second column was for the pore water pressure. Okay, so 0 meters, minus 1 meter, minus 4 meter, minus 6 meters, and minus 9 meter. So at 0 meter it was 0. Minus 1 meter it was minus 49.05. Minus 4 meters it's minus 19. At 6 meter depth it is 0. And at 9 meter depth it is 29.43. If I join all these by a straight line, so I should get, this whole thing invariably gives me a straight line. I can use a ruler and join. Now the question is, what happens above this level? Now there are two school of thoughts. You can actually, from here, because surface is 0, some of the students are bright students, they join this to this level. They say, above this there is no capillary. Okay, you could follow this. There is no harm. Even that answer is correct. But you can also be less conservative by joining this straight line over there. So from there to there, it's linearly, it decreases. It's either way you can follow. There's no harm in following any of the two methods. So the difference between the two was the effective stress. That's the last column, and I would like you to plot this, the last column as well. Remember, all the three stress distribution are to the same scale. So it's quite appropriate to choose the correct scale so that you have a nice plot. You can use a graph paper as well if you're quite happy with using graph paper. Okay, so this concludes this question number 2, and probably this was problem sheet 3. Let's go back to in continuation to our lecture. Okay, if you have any questions, please raise your hand. Okay? Like I said, this is an interactive session. If you don't raise hands, I will not get my salary. Okay? Right, we'll continue with soil, with this section on soil and water, and the next is soil permeability. Okay, we have VCE teacher with a question. I'll just come to this question in about 10 minutes. Let me just quickly start off with this section. Okay, but your question is there. It's there on my screen. Yeah, but I'll continue. Okay, now for most flow, we say the soil flow is laminar. Okay, I hope you, in your fluid mechanics, you may recall laminar flow, I think, is with Reynolds number less than 2000. Okay, so when the flow is laminar, we say that, you know, this is where the soil permeability will be described. So this permeability is the quantity or the easiness with which the water flows through the soil. And this quantity or the number is something which we will explore in this section. Okay. Let's look at the very first test which was done by Darcy. Okay, this is a figure which has been zapped from Darcy's work. So the shaded region is the sand column. Okay, is a column which contains sand, and say it's a cross-sectional area. So assume an area of A. It doesn't matter if it's square or rectangle. Rectangle may have corners, but let's say it's a circular one. Okay, with a cross-section area A. At one end, okay, you have a water reservoir. What do you mean by reservoir? It just shows that this level will remain constant. So the triangle, inverted triangle, shows the upper level. So it is being continuously being filled with water, but because of some overflow mechanism, this height will be remained. It will never go above this level. Okay, so that's the water reservoir at one end, which is 1. At the second level, what Darcy did was he had another reservoir. Okay, again with an overflow mechanism, that is the with a shorter height, meaning the difference in level between the two reservoirs, Darcy kept it as delta H. Okay, if you look at the sample, the length of the sample was L. Okay, and the cross-sectional area we just said is A. At the two ends, right next to the reservoir, Darcy inserted some standpipe. Okay, Thank you. So Darcy inserted standpipes at both at this reservoir as well as the other reservoir. If you remember your elementary, elementary flow mechanism, if there is no flow, and if I have inserted this standpipe right up to the middle of this level, okay, the water level in the standpipe as well as the reservoir should be the same. Okay, there is no this tells me what is the height of water, which is H1. Similarly, a second standpipe inserted right next to the other reservoir gives me the height of water as H2, measured from the middle of the soil. Okay. Now, having done this, Darcy did experiments which were both based on one-dimensional flow as well as two-dimensional flow. In this section, we will only concentrate on one-dimensional flow. Okay. So in Darcy's experiment, if you look at the same figure, this is the same figure but zapped on the top corner. Okay. What is the total head? By definition, okay, if you have done your fluid mechanics, I believe, total head is also called as total potential. It equals to the sum of pressure head plus the elevation head plus the velocity head. So the total head at level 1 should be the pressure head plus the elevation head plus the velocity head. Okay. However, the velocity head is more for all soil mechanics problem. It's conveniently taken as 0. Or it's ignored. So because it's much smaller than the pressure head and the elevation head, so we ignore the third one in most cases. Okay. Let me just move on. In other words, the total head equals the pressure head plus the elevation head. Let's look at this first same figure. Please do not look at the text, the bottom text. Look at the figure on the right again. What is the total head at 1? Okay. Just to remove the bottom one, and let me go back so that you don't read the bottom text. The total head at 1 equals the pressure head. What is the pressure head at 1? Is the height H1. H1 over which the water rises, that's pressure head. What about the elevation head? Now for elevation head, I need to assume a datum. I can take a datum somewhere there. I can take a datum at the bottom of the slide. I can take the datum at the bottom of your classroom floor. I can take it anywhere. In this case, I have conveniently assumed the datum to be this level, which is 1. Okay, somewhere when. So at the center of the soil is the datum, that's 1. So if this is datum, so the second part, which is the elevation head, equals to 0 because this is datum. So at this level, my pressure head is H1, elevation head is 0. Velocity head we have ignored. What about the second one, total head at 2? Okay, the pressure head is H2 because the water in the standpipe rose up to a level H2. The elevation head, now this is my datum. I cannot change the datum for a same problem, have two datum. So this was the datum. So the center of the soil above the datum is H0. Okay, therefore the total head at 2 would be H2 plus H0. Okay, now total head at this point 1 was H1. Total head at 2 is H2 plus H0. Let's now go to the next slide. Okay, the next slide is what is the potential difference or the total head difference. The total head difference between 1 and 2 will be the thing which causes flow. So total head at 1 and total head at 2, the difference is what causes the flow. Total head at 1 is H1, correct? Total head at 2 equals H2 plus H0. That's over there. Okay. Let me see, right click and see this is, oh, oops, sorry. You can now download. I forgot to right click and allow download. Now this file is downloadable. You can please download the file. Okay. Come back to this one. So the total head, the potential difference or the head difference which causes the flow equals H1 minus H2 plus H0. That's over there. Okay. If you look at this carefully, this length minus length from there to there. Okay. If you look at the screen carefully, that this length minus this length should be this difference delta, which is shown by delta H over there. In fact, H1 minus this whole thing is a delta H. If you look at this figure carefully, delta H is the difference between the two water levels in the two reservoirs or the standpipes. Okay, so can I just put it in simple English that the potential difference which will cause flow or the total head difference which causes the flow equals the delta H, which is the difference between the two water levels. Okay, so if I want to know the flow between A and B, I just deduce what is the difference in the water level between A and B. Okay, so move to the next slide, please. So Darcy, what he did was, in the same setup, he varied delta H, he varied L and A. The length of the sample was varied, the cross-sectional area of the sample was varied, and the head loss between the elevation 1 and 2. And he got out a relationship wherein Q, which is flow. Okay, remember Q is the flow and it has units of volume per unit time. So its flow, it was found to be proportional to delta H by L. Okay, wherein was found to be proportional to delta H and also A, and I'm sorry, it was inversely proportional to L. So directly proportional to delta H and A, but inversely proportional to L. When Darcy opened up this relationship, he found out a constant K. Okay, K was a constant which was defined as coefficient of permeability or simply called as the permeability. Some of us like to use the term hydraulic conductivity. It's the same as permeability for our engineering purpose. If I move to the next slide, so if you look at this carefully, delta H by L, okay, is in fact the head loss over the length of the sample. Okay, this delta H by L is your hydraulic gradient. Okay, you've probably done this in fluid mechanics. Delta H by L is the hydraulic gradient, normally represented by I. So if this is replaced by I over here, I get Q equals to KIA. Okay, Q equals to Kia. It's easy to remember. Q equals to KIA or Kia. If I look at this expression Q equals to KIA very carefully, okay, Q divided by A, I take this A over there. What is Q divided by A equals to KI? If I look at the dimensions of Q by A. Q is meter cube per second. Okay, it probably has units of meter cube per second, and area is meter square. As a result, I have dimensions of velocity. So left hand side is replaced by velocity over here, and the right hand side remains Ki. Okay, I'm going to look at this again very carefully in the next slide. Okay, I have over here velocity equals to Ki. So in other words, can I say K, we said, is the coefficient of permeability? Can we define K as the velocity? Okay, over here this velocity we say is the superficial velocity. So can I define permeability as superficial velocity per unit hydraulic gradient? If V is the velocity per unit hydraulic gradient. Why we call this as superficial velocity and not velocity? Okay, superficial because the flow in this case we say it assumes to occur over the entire cross-sectional area A. Okay, the entire tube. But if you look at the tube has soil in between, and the flow only occurs through the voids, through the gap in between the soil particles. In other words, the flow will never occur under A. It only occurs under a smaller area. That is why we call this as superficial velocity. Okay. So if I extend this concept of this velocity over here, the superficial velocity, okay, I get flow which is Q. It was defined as V times A. In this case, it's superficial velocity times A. It occurs through the void. So can I say flow through the Vs? That's the seepage. It seeps through the voids times the area of the voids. Okay, if I look at the cross-sectional area of the flow, the Vs times As is the seepage velocity times the area of the voids. The flow actually occurs through this area. It is the same flow which we say occurs through the area of capital A. That means, if you look at this expression very carefully, I get superficial velocity times the entire area of the soil equals the seepage velocity times the area of the voids, assuming that you're looking at the cross-sectional area per unit length. So the length which comes out and hits you is 1 unit. Okay, so this area, can I say V divided by Vs? Okay, this equals to area voids divided by the total area. Okay, if I say if I times the 1 unit which comes out and hits you gives the volume. So the area of voids is volume which comes out and hits you. Similarly, the unit length which comes out and hits you equals to total area times unit length, which gives you the volume. If you recall your first lecture, volume of voids to the total volume is the porosity. Okay, so I have V, which is the superficial velocity, equals to the porosity times the seepage velocity. Porosity is always less than 1. So can I say seepage velocity will always be greater than the superficial velocity? Okay. Let me move to the next slide, please. Okay. The measurement of permeability is done in the lab and the field. In the next lecture, we will do the laboratory measurement. Field measurement is something which is beyond our scope. We will not do it, at least for these video lectures. But I leave it to your individual institutions if you would like to do the field test. But laboratory test is something which we will do in the next class. Okay, we'll take the questions. We have 5 minutes. We'll take the questions. The very first question comes from DCE teacher. Okay. Okay, we are with you. I am sorry, there is no audio. Is it our problem?
No, 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 their problem.
U is equal to WG by SR.
Kindly check the
I
online.
apologize, no audio, I can't hear you. I can only see your smiley face. Thank you. There's no audio. From U is equal to WG by SR. From interrelation. Can you call them? Okay, I have people over here who say, please check your audio. Okay. From interrelation. Okay, could you?
Do you hear me?
No, I can't hear you. Can you please check your audio and maybe we'll come back to you in 2 minutes? Is that fine?
Yes.
Please check your audio. Okay, now we are with TKMKL.
Sir. Hello, sir.
Yep, we can hear you.
Yep, we can hear you. Sir, I have a question. My question is, which soil is having more permeability? Is it the dispersed soil or the flocculated one?
All right,
That's quite interesting. Hello, please, we might hear some distance because we are getting it from your side.
Okay.
Okay. So can you hear me?
Yeah, we got the
Yeah,
question.
we got the question. People say switch off your mic. I can then reply back.
Okay, thank you.
Okay, thank you. So your question was,
Please switch off your.
can you switch off your mic, please?
You're getting echo from your
You're
side.
getting echo from your side.
Okay.
Okay. Start.
Why stop?
Echo is there, not stopping, sir.
Oh, at least let me answer the question.
Yeah, you can answer. They can listen you, sir. They can listen you.
Okay, please don't touch the mouse, okay? Okay, the question was, okay, somehow the gentleman over here feels that, the echo was too much, so he has disconnected this, but I can repeat the question. The question was, which soil will have more permeability? Whether it is the dispersed soil or the flocculated soil. Okay, let me just draw this on a figure, okay, to explain this. Okay. Now, a flocculated one will have randomness. A dispersed one has an order. There is some orderly arrangement. Okay. So if you look at the flow, we have done this. The flow in this direction and this direction are more or less similar. And if I want to follow the flow in this direction, it's also tortuous. So can I say this flow is comparable to this flow? So the flow K vertical or K horizontal in this soil is comparable to K vertical in this soil. So this for dispersed fabric, if the flow is in this vertical direction, your permeability value will be comparable, meaning the order of magnitude should be similar. However, if the flow is in this direction, remember the horizontal flow, the flow is very convenient. It can simply, bypass all the soil grains and go horizontal. So K horizontal will be much greater than K vertical. So in other words, this flow will be much faster than the flow in the other two. Okay? I hope I was able to answer your question. Okay, now we are at DCRU teacher. Yes, please.
Sir, we are unable to get your audio. Can you please check the settings and sir, your audio is not coming, sir.
Could you please write down your question on the chat window? I'm sorry.
You can put your question in your chat window.
Or maybe check your audio system. Okay.
And check your mic is whether mute or not.
I'm sorry, there is no audio. So can we come back to you again? Or maybe check, you can put your question on your audio. Okay, we are at VCE teacher. Yes, back to VCE now.
Madam, still there is no audio is coming from your side. Can you please check the mic settings?
How can two centers have same problem? Is it some other, maybe there's some genuine problem?
That's because of their side only.
I'm extremely sorry, we cannot hear a word. Can you please write down your question on chat window? Can you please arrange for that? I'm sorry, VCE teacher, please write down on the chat window. Okay, you say okay, I have one question by DCRU teacher. I'm not sure if the question is complete or whether it's just a comment. It says in the stress diagram, which was, which could have been drawn by the brilliant student, the pore water pressure comes into picture after a depth of 1 meter. Yes, this is true. This was true. Okay, I have the diagram over here. Where is the diagram? Where is the figure? Sorry. Stole my paper. This was the figure. So that was the pore water pressure distribution diagram. So if I want to redraw this for the brilliant student, it probably went something like this. Okay, and went horizontal. Yes, that was the thing. Yes, the diagram, then, okay, the question continues. It says, therefore, the diagram of the effective stress would be the same as that of the total stress up to a depth of 1 meter. Then thereafter, there would be a sudden, okay, the question is coming in pieces, but your comment is very correct. From the fundamentals, E equals to WGS by SR. I think you're getting some, you're mixing up the equation. Your question, okay, is on, let me just continue with the question of VCE teacher. VCE teacher has a comment that, if void ratio is related to degree of saturation in the soil above the capillary saturated soil, if degree of saturation is 0, your void ratio would become infinity. That is incorrect because your water content also would not remain the same. Okay, your water content is related to degree of saturation. So that expression of yours is not valid. Okay, I would like you to go back and please look at the expression carefully. The denominator in that expression, the denominator which is SE equals to WGS, if S becomes 0, your water content would also become 0 because there is no water. Okay? Okay, there's another question from PKM KL teacher.
Hello, sir.
Yes, we can.
Yes, we can hear you. Sir, why this Darcy's law is not applicable or valid in the case of colloidal clays?
Sorry, repeat the question.
Why Darcy's law is not applicable or valid in case of colloidal clay?
The question switch off the mic. End of the mic and it won't come back. Okay, thank you. So the question is switch off the mic from the main audio. Okay? See, it's still coming right. You have to switch off the mic from the Okay. Your question is why is Darcy's law not valid for Okay, I'll repeat the question. The question was if Darcy's law is valid for colloidal clay. I guess that was the question. Now Darcy's law is valid for measurement of permeability right up to 10 to the power of minus 11, 12. So I do not understand why you say it's not valid. It is valid. It is very well valid. Only thing is it is not valid when the flow is turbulent. Turbulent flow will occur when your grain size distribution, when you have boulders, cobbles, when the flow occurs through boulders and cobbles. In that case, Darcy's law may not be valid. But for fine grained particles, yes, Darcy's law is valid. Okay, was that the last question?
Is there any questions? If you have any question, please hand raise. Or else keep in chat box.
Okay, before I conclude, next time I would like, whenever you ask a question, my suggestion from my team is, after your question is over, when it's over, switch off your audio from the main, junction box or somewhere there. Mixer? You call it mixer. So please switch off the audio from the mixer. In that case, what happens if you don't do that, the reply over here goes to you. Then from your audio it comes back to me and everyone. So we hear my voice twice, and we don't want like that. I don't want to hear my voice twice. In fact, no one would like to hear me twice. Okay, so please follow this. We will come to our conclusion of this session. I would like you to please post any question you have on either by email to me, or maybe leave it for the next time. Please ask questions because it also helps me to improve. Okay, I also have to go back and search into textbook into what really how the question can be answered in the best possible way. Okay, thank you very much. We conclude today's session.